This is the machine I'll be talking about today. This is a 5-axis mill, which has a interferometer built into it. So you can prepare your device. Let's say you have a PC board, a motherboard with a BGA package on it. Rather than having to remove the device, thin it, and then solder reflow it back onto the board or socket it back on the board, you can actually do the prep on the board, do the measurements on the board for how thick the silicon is, and take images of the part and even electrically test the part in certain cases. We have image overlays where you can import x-rays, curvature compensation, and mesh mapping, which go together. Something that makes the machine very unique is you can dispense the cooling liquid and suction the cooling liquid off of the die without getting it on the board. And so this is very useful in that you could actually have the device functioning using the liquid as a coolant, functionally test the device, and then determine how thin you could take the silicon if you were trying to evaluate a process, for example. This is the overlay capability. So you load an overlay, you scale it to fit. That overlay could simply be a photograph you previously taken of a device that has been decapped or decapsulated. Or you could import an x-ray, or it could be a CAD drawing. Anything that you want can be overlaid and shadow aligned to the actual product that you're going to be thinning or working with. There's a 1 and a 2 spectrometer system. So it works basically the same way, except with the dual spectrometer, you can have the machine automatically switch between the spectrometers depending on how thick the silicon is. So generally speaking, if you are 8 microns or thicker, you're going to be using the NIR spectrometer. And if you're less than about 10 micrometers, there is an overlap, then you're going to be in the visible light mode all the way down to 8 nanometers. So for curvature modeling, there are several methodologies here that we use. Being able to give the system a curve model, usually it's an R-squared model, you can plug in those values and just simply model that surface. If you add into that the mesh model, then you get the best of both worlds. So you have curve to take care of the majority of the error on the part, and then you have the mesh model to be able to fine-tune the irregularities that may occur because the package is warping as you thin a sample. So combining these techniques, you have curvature modeling, adaptive mesh mapping, and something called SURF, which is a force control mode. And so SURF, what it does is if your part is pliable, if it tends to flex or move, then what SURF is doing is you can actually tell the machine how much flexure there is in the part, and it will countercompensate that flexure in order to give you a surface that actually follows the profile you're interested in. So some new imaging capabilities that we're adding, what we're going to end up doing is have the IR cameras be in all camera positions. So you'll be able to image in 45 process using 940 nanometer light to see through thinner silicon. So 100 microns or less, you'll be able to see readily through the silicon. Also, if you're dealing with epoxies, which are infrared transparent, then you can use the infrared mode to see those epoxies for targeting when you're going to thin. So you can do this with the process camera, which can actually see where your tip is while you're thinning. You can also do this with a target camera. This is an image of the roadmap that we're taking to do the infrared imaging. So the image on the left is the visible illumination on the same camera that also is sensitive to the near infrared. So we switch illumination sources to go between visible and infrared. And so the image on the right, you can see the circuitry patterns visible through the translucent silicon with the 940 nanometer illumination. So I think at this point, I will give ourselves some time for some questions. And I would just like to thank all of you for attending.